Hey, good afternoon. Today, I'd like to continue our study in physics, especially in electric physics. Today, we will discuss about the Gauss law and electric potential. After we discussing about the charge and the electric fields, some of the material in the electric fields and charge we will use in this subchapter, Gauss law and electric potential. And the first, we have to know what is the definition of electric flux. The electric flux, this is the notation of electric flux, through a surface is the amount of electric field that pierces the surface. So if we have the electric fields like these ones, so the electric fields is you know that if we have the charge, like positive or negative charge, so the area around the charge, we can calculate as an electric field. So um, the something around the charge, either is positive or negative, so we call it electric fields. So if we have the electric fields and we have the surface like these ones, so this is the electric field. So the amount of electric field in the surface is electric flux. And then the area vector of dA for an area element or spatial element on a vector on a surface is a vector that is perpendicular to the element that has a magnitude equal to the area dA of the element. So, okay. So if we have the illustration of electric field like this one, and then this is the surface. So the vector of the surface is like this one. So this is the vector of the surface, the A. So the electric flux is the E, or the electric field multiplied to the dA. dA is the surface, the vector of surface. So the electric flux through a patch element with the area vector dA is the given by a dot product. So this is the electric flux. So we can easily by multiply the electric field and the area of vector or dA in the some spatial area. So if we have like this is the rectangular and this is the 2 centimeter and 2 centimeter, so we can calculate what is the A. What is the A? A is the surface of the object. So by using the dot product it's mean that we have to know the direction of the electric field through the surface. It's like this one. If we have the electric field, this is the vector of the surface or the A, and the electric field I put by using the another color like this one, and we have the electric field E like this one, and the angle between the electric field and dA is like 30 degree. So by using this one, we can use the dot product. Dot product it's mean that for this condition, the flux is A dot dA cosinus theta. The cosinus theta is the angle between the electric fields and the vector of surface. Okay, I hope you can follow this explanation. So this is the D flux. So the D electric flux. So if we want to calculate the total flux through a surface, so we can use this one. So the before is the D flux is E A E dot dA like this one. So if we make an integral in the left side or the right side, we can get this one. So the flux or total flux is integral of electric fields and dA. So we can carry it out over the surface. And then the net flux through a closed surface, we can call it the Gauss law, like this one. So this is the flux and our total flux in the surface. And then, so if we have a charge like this one, this is the charge, and then around the charge we can calculate the electric fields. So a Gaussian surface is like this one. So the area outside of the charge, so uh, we can call it the Gaussian surface. If the electric field is away from the positive charge like this one, so this is the plus key. And then if the electric field is like this one, so this is not too okay, it's like this one. The gap between one electric field line and another electric field line is far away like this one. So the charge is not very large like this one. If we make assumption that this is the plus key, so if the gap between the line of the electric field is shorter like this one or smaller like this one, so the charge is plus 2 key. And please remember that if the charge is positive, so the electric field line will be like this one, away from the object. But if the line or electric field line come to the charge like this one, so it's mean that this is the negative. So if this is the positive key, so what is this one? So this is a minus, and this is the 4, and this is 1 2 3 4 5 6 7 8. So this is a half of the positive key, so a half of key like this one. Okay, so in my first explanation, I explained this one. So if we have the surface like this one, this is the A, B, and C. The first one, if the surface, this is the electric field, E. So I change to another pen color. So, and this is the vector, this is the X, and this is the Y, and this is the also the vector of the surface. So how to calculate electric flux? So we have to measure the angle between the electric fields and also the vector of the surface like this ones. So you remember that I explained before, this is the angle between the electric field and the surface. So we can easily get the delta flux is AE cosinus theta multiplied by delta A. Where the delta flux is the flux in some specific area, and delta A is specific area or specific surface in the object. So if we want to know the total flux in the object, so we have to make an integral, or in this explanation, or in another way, we make a summation of many delta A, so we have the total flux. Or so we can use this equation to explain this is the total flux of the object. Okay, and this is the delta A, or the surface. So it's like this one. If we have the E, or electric field, is 2k Newton per coulomb, has a positive direction of the x-axis, determine the flux through 10 centimeters square as illustrated in the picture. So in this exercise, so we have to use these equations. The flux is E dot dE, or the E E dE cosinus 0. Why is 0? Because the direction of E and direction of a vector of surface is equal, like this one. So this is equal. It means that there is no angle between the electric field and the surface. So the cosinus theta or is cosinus 0. So E is 2 kN, so kN per coulomb. So 2 multiplied by 10 over 3, and then the surface is 10 centimeters square. So we uh, change from centimeter to meter, and then we got the total surface, so we can calculate the total flux in this exercise. Okay, and then if the direction of the E is changed like this one, so we can use also the same or similar equation here, but the cosinus theta is not 0, but this is the 30-degree 0, the 30 degree. So we can get this flux like this one. Cosinus 30 degree is a half of a square 3 square. So we can get this result. And then to determine the electric flux, so we have to use the closed surface like this ones. So if we have this is like this one, this is the object here, this is the object here, and then to determine or to calculate the total flux in this object, so we have to we have to check a small part of the object like this one. So we have to check the flux in 1 and in 2 and in 3 like this one, and then we make a summation of total flux in the object. So it's uh, like this ones. And it's saying that an inward piercing field is negative flux, and outward piercing field is a positive flux, and then skimming field is a zero flux. So the total net flux or total flux is closed integral of E dot dE. Okay, so how to solve this equation? So we can check here. This is the surface. So this is the E, the direction of the E, and this is the vector of the A, like this ones. And then in this area 3, so this is the E, and this is the delta A. So we get the positive flux, and here we get the negative flux because the direction of the E and the delta E is in opposite way. So we can very easily uh, determine that, or we can easily get that the flux is negative. But if we can call in the second like this one, if the angle between the E and delta E is 90 degrees, so the flux is 0. So by using, we make some summation of total area in this object, so we can calculate the total flux. Okay, so this is the checkpoint 1. The figure here shows the Gaussian cube of area A in a uniform electric E that has a positive direction of the z-axis. In terms of E and A, what is the flux through the front face, which is in the xy plane? So this is the surface here, and then B in the rear face, and then the top face, and then the whole of cube. So to calculate the E here, so the first in front face, so this is the E, and this is the also the E. So the total flux is A dot E dot A, right? E dot A cosinus theta. But because of the direction of E and A is 0 or in similar directions. So the total flux is E dot A. This is in front phase. This is the answer of A. And what is in the rear phase? In the rear phase, it means that in the behind of XY plane. So in the rear phase, the vector of A is here, and then the electric field is here. So the E and A is opposite direction. It means that the cosinus theta is 180. So in B, so the total flux is E dot A cosinus 180 degree. So it means that cosinus 180 degree is -1. So we have the minus EA. So this is in a rear phase. And what is the top phase? Top phase like this one. So in the top phase like this one, so this is the A and this is the E. Right? So the angle between the E and A is 90 degrees. So the C here's flux is EA cosinus 90 degree is 0. So in the top phase and also in bottom phase is in similar 90 degree, and also in here in left side and also in the right side. So what is the D? So the D is whole cube. So you have to make a summation of the total flux in the front phase, rear phase, top phase, bottom phase, left phase or left side and right side. So you can calculate by yourself. This is the EA and this is the negative EA. Okay, so the total is 0, right? Yeah, and then this is the electric flux here. Example, this is a cylindrical Gaussian surface closed by end caps. So what is the net flux of the electric field through the cylinder? So it's similar to the previous example like this one. So to solve this equation, so we have to calculate all the sides of the Gaussian surface like this one. So in here, what is the total flux? And here, what is the total flux? And also in the surface of the cylinder surface like this one. So uh, we can know what is the total flux. So we can see in the front face like this one. So the total flux is A dot A. So in here cosinus theta, because of the direction is similar. So this is the flux is EA, and then in the left in the so in this side the flux is minus EA because of the direction between E and DA is the 90 degrees. So the flux here is minus EA. And then in surface, because of the all in surface, the angle between the E and DA is 90 degree. So the total flux is 0. So the total flux in the cylinder is 0, right? Because it's similar. So this is here is positive EA, negative EA, and in surface is 0. Okay. And then this is the Gauss law. The Gauss law related the next net flux penetrating a closed surface of the net charge of K and A and C enclosed by the surface like this one. So the epsilon 0 dot net flux is K ENC. So Gauss law also we can write in terms of electric field. So we can use the another definition of the flux. Flux is a surface integral of E dot dA. So we can get this formula from this formula. So the Gauss law is saying that the epsilon zero dot surface integral of E dE is equal to key enclosed. It means that if we want to calculate the total key or total charge in some object, so we can use these equations. This is the total charge in the object. So we can know by using the flux and also the epsilon zero. Just like this one, we have the object like this one, and in this object we have two charges. This is the positive charge and this is the negative charge. Okay, and then we can check what is the total of the key enclosed by check all the surface like this one. This is the S1, and then we check in S2 and S3 and S4. In S1 is enclosed by the positive charge, and S2 is enclosed by negative charge, and S3 is enclosed no charge, and S4 is both charge and this are no net charge. So by using this one, and then we make integrations of total flux, and we multiply to epsilon zero, we get the total of charge. Okay. So we have another problem here, figure 23.7. So five charged lumps of the plastics and an electrically neutral coin. This is electrically neutral coin. The cross section of the Gaussian surface S is indicated. What is the net electric flux through the surface if Q1 equal to Q4 is plus 3.1 nanocoulomb, Q2 equal to Q5 is minus 5.9 nanocoulomb, and Q3 is minus 3.1 nanocoulomb. So the key idea is the net flux through the surface depends on the net charge enclosed by the surface S. So the coin doesn't contribute to the flux because it's neutral. So we just calculate the Q1, Q2, and Q3. Q4 and Q5 is outside of the surface. This is outside of the surface. So we also didn't calculate the Q4 and Q3. So the key ENC or key enclosed is the only a summation of Q1, Q2, and Q3. So we can get that we back to this one key and key enclose is epsilon zero dot flux. So this is like epsilon zero dot flux is the key enclose. So here, so the flux is key enclosed per epsilon zero. So we use this equation here. So flux is key enclosed per epsilon zero. So in the surface on the Q1, Q2, and Q3. So Q1 plus Q2 plus Q3 per epsilon zero. So don't forget to put the positive and negative because this is a total charge. So this plus Q1 is plus 33.1, and then Q2 is minus 5.9, and Q3 is minus 3.1. So we can get this equation. So we get the total flux is minus 617 Newton meter square per coulomb. So the minus sign shows that the net flux through the surface is inward, and thus that the net charge within the surface is negative. So yeah, the minus sign, so the net total flux is through a surface is inward. Why inward? Because the net charge of the surface is negative. So something like that. And then this is the relationship between the Gauss law and Coulomb law. So we get the Gauss law before like this one. So epsilon 0 dot in the surface integral of E dE is equal to K enclosed. So we can get by using this one. Epsilon 0 dot integral surface integral of E dE is K enclosed. So if we because E is the constant, so we just calculate the integral surface of dA. So we can make like this equations. So if we put the Gaussian surface is like a ball, so the integral surface of dA is 4 phi r squared. So the key enclosed is epsilon 0 E 4 phi r squared. So the E is equal to 1 over 4 phi epsilon 0 dot key per r squared. This is like Coulomb's law. So we remember that E is key per r squared. So it's similar to this one. So to determine the electric field, we can use the Gauss law or use the Coulomb law like this. And then this is the charge isolated conductor like this one. This if we have the charge like this ones, and this is the surface. This we call it the Gaussian surface. So this is the negative here. So the negative will attract the positive like this one. So this is a positive ion here, and this is the negative ion. So the positive charge is distributed in inner wall of the cell, and the negative charge in outer wall. And then this is the charge isolated conductor here. If the charge and key enclosed when the Gaussian surface lies on the conductor surface in an area of A, like this one. So this is the charge of Gaussian surface enclosed by the conductor in area of A. So if C, like this one, is the charge per unit area, then key enclosed is equal to C dot A. So when we substitute CA for the key enclosed and EA for the flux in the Gauss law, so we can use this one. Epsilon 0 dot E dot A is equals key enclosed, and key enclosed is C dot A. So we can put off this one. So E or electric field is the C per epsilon 0, or this is the conducting surface. So it's like this one. So if we have the situation like this ones, so we can calculate the E by using the C per epsilon 0 here. And then the second, if we apply to cylindrical symmetry like this one, so we back this flux is E A cosinus 0. It's like this one. This is the Gaussian surface, and this is the very long uniform charge like this one, positive plus. So the total flux is this is the Gaussian surface here, and then the surface is 2 phi r. R is the distance between the center to the Gaussian surface. So to determine the E or the electric field, we can use the Gauss law like this one. So E A cosinus theta. So we replace the A using the 2 phi r dot h. Yeah, this is the h. So the area is like this one. So it's like the area of cylinder, and cosinus theta, because the direction of E and the direction of the A is equal. So there's no difference, no angle difference between the dA and E. So we can get E dot 2 phi RH. And then the epsilon 0 flux is equal to key and close. So we can replace the flux by using this one. So we can write like this one, epsilon 0 E multiplied by 2 phi RH is equal to lambda H. And the lambda H is the key and close. Why the lambda H? Because this is the H is the charge of this very long charge like this one, and then H is so is this one, the H of cylinder. So this is the key enclosed is equal to this one. So key enclosed is equal to lambda dot H. So the total of E or electric fields is lambda per 2 phi epsilon 0 R. This is the line of charge. So we can determine the electric fields by using the Gauss law, like this one, for the line of charge. And then the second is planar symmetry. You remember the first, this is we open here, and then this is the close. It means that the E is equal to 0. But here in the planar symmetry, the in the rear face like this one, the E is not a 0 like this one. And we have to calculate in the right side and also in the left side. So again, using the Gauss law, using this one, epsilon 0 dot surface integral of E dE is equal to key and close. And then because of the E, and this is the E or the electric field, and the direction is the opposite to Y like this one. So this is the positive. So this is the E is come to this one and E come to this one in another side. So the total of flux is EA plus EA because of this side, the first EA, and this is the side is second EA. And then key enclosed is this one, C dot A. So we can put this one off. So E is equal to C per 2 epsilon 0. This is the seat of charge. So like this one, this is the exercise for the seat of charge. And in this figure, 23.17a, so portion of two large parallel non-conducting sheets, each with a fixed uniform charge on one side. The magnitude of the surface charge density are C plus this one is 6.8 microcoulomb per meter square, and then the density of negative charge is 4.3 microcoulomb per meter square here. And then find the electric fields to the left of seat. So in here, this is the left, and then between seat, and then this is the right seat, like this one. So on the first, don't forget to check the kind of the charge. This is the positive here, and this is the positive here, and this is the negative here. So at any point, the electric fields due to the positive seats is directed away from the seats, and from the equivalent. Okay, so the magnitude. So we using this equation because this is the similar to the problem. So the E plus, so E plus is from the positive charge. So this is the E plus. So you can see in B. So this is the E plus, this is the E plus, and also here is this is E plus because the direction of E plus is away from the positive charge. And then the second is the direction of E of negative charge is come to the negative charge. This is the in right side, between side, and this is left side. So don't forget to check all the sides here we have the left, between, and right. So you have to check all the total E in this chart. So the E plus is the density per 2 per this one per 2 epsilon 0. So the density of plus is 6.8 multiplied by 10 point minus 6 coulomb per meter square per 2 multiplied by 8.85 multiplied by 10 point minus 12 coulomb square per Newton meter square. So we can get this 3.84 multiplied by 10.5 Newton per coulomb. And then for negative also we use the similar equation. So we get 2.43 multiplied by 10.5 Newton per coulomb. And then the force in the left side, so left side is EL, like this one. So because of in the left side, you can see in the figure B that the positive and negative charge is in opposite direction, like this ones. So the EL is E plus minus E minus. So E plus is 3.84 and A minus is 2.43. So we get 1.4. Okay. So because this is the positive, so the direction of the AL is like this one, is similar to the positive E. And then in the between, we can check in the B that the position of direction is similar. So EB is E plus plus I minus, so we get 6.3, and the direction is yeah, this is the right way because this is positive, similar to the I plus and I minus. And then for the right side, that is similar to left side. We have to we have to use this is the right, so I plus minus I minus, like this one. So similar to this one, and we can see that the result is similar to EL. So this is 1.4 multiplied by 1.4 multiplied by 10.5 Newton per coulomb, and the direction is similar to the right side. So this is the total electric field in the left side between and the right side. And then for the spherical symmetry, like this one, determine the E inside and outside the spherical shell with the radius R and uniform charge with total charge of Q. So the outside of the cell, so we can use the flux in the surface integral E dE or EA or E dot 4 phi r square is equal to K per epsilon 0. So it's like the before this explanation. Flux is K per epsilon 0 or K enclosed per epsilon 0. This one. So the E is equal to 1 per 4 phi epsilon 0 multiplied by K per r square. It's like a column law for the outside of the cell. And then for inside of the cell, like this one, we know that this is the spherical symmetry. So the total of K is not equal to the K in. K in is like this one here. So the key inside of the cell is not similar to the total or key enclosed. So we can make a similarity between a key n and a key large key. So the key in is cell volume of R, like this one, R small r per cell volume of R large R, like this one, dot key. So we can use this equation. So small r for 3 bar by big R for 3 dot key large key. So we can solve this equation by using the total flux. So we can get E is equal to K per 4 phi epsilon 0 dot R per R over 3. So it's like this one for the spherical symmetry. Okay, I hope you understand of this equation. So just know what is the small r and what is the big R here. And here, as we just check the distance between the point, like this one. This is the P to the center of the surface. Okay, and another is electric potential for today. So remember, we have to remember force, electric field, and work. So it's like particle 1 is located at the point P in the electric field of particle 2. So electric force is conservative and thus has an associative electric potential energy. So the change of delta U in the electric potential energy U of a point charge as the charge moves from initial point to final point of electric field. So it's like if we have a charge and then the charge is moved from one side to another side in similar electric field. So we can measure the electric potential energy. So the delta U or electric potential energy is UF minus UI. UF is the final point and UI is initial point. So we get the minus W. So what is the chance of U in the electric potential energy of released electron when the electrostatic force goes to move vertically upward through the distance d? Like this one. So note that with in the previous explanation, delta U is minus W. So W is we have the negative charge like this one, and then move to vertical. This is the final point, and this is the initial point. So it's the F, and this is the I. So the work or W is F dot D, and then F is key dot E. So the W is key E D. And then we have, because it's the factor, so we must put the cosinus 0. This called the theta is the angle between the direction and E and D. So we get this one. W is key E D cosinus theta. And then the electric potential phi at the point phi is U per key. And then the potential difference is delta phi is Vf minus Vi is equal to minus W per key. So if we know that what is the work or what is the potential energy, we can calculate the electric potential by using the work or the electric energy per the charge. So like this one, calculating the potential from the field, like this is the initial point here, and this is the path, this is the electric field, and this is the final of F. So the dW or the work of the charge is F dot ds. F is the force and ds is the actual path of the charge from initial point to the final point. So the dW is we can put the F is key 0 e dot ds. So if we make integration of this equation, we get that W is key 0, it is constant, and integral from I to F dot E dot ds. And we note that delta F is Vf minus Vi is minus W per key. So Vf minus Vi is equal to minus integral I to F E dot ds. Okay. Why we get this equation? Because you know that this is the Vi minus Vi is minus W per key, and then we can use this equation. Minus W is minus key 0 integral I to F E dot ds per key. So we can make this one. So this is a minus I to F E dot ds. This is the delta F. So if Vi is equal to 0, then F is this one, minus integral I to F E dot ds. And this is the example. So figure 24.5, a test charge of key 0 move in straight line from a point I here to point F here along the direction of A along the direction of A, uniform external electric fields. B. Charge key 0 move along path I, C, F in the same electric field. Okay, so this is the initial point, and this is the F. Okay, the first the from I to F. This is the A. So and the question is find the potential difference between Vf and Vi by moving a positive charge K0 from I to F along the path zone, which is parallel to the field direction. Okay, so we can solve like a E dot ds. So E dot ds cosine 0 because of the D and the electric fields is in similar direction. This is the D, this is the D, and this is the E in similar direction. So cosinus theta is similar to cosinus 0 is equal to 1. So E ds. So Vf minus Vi is minus I to F E dot ds is equal to minus EF E ds. And then we can put off the e because this is the constant like this one. So just make integral from I to f ds like this one. And integral I to f is d. So Vf minus Vi is minus Ed. So this is the result if we move from the initial point I to f directly for vertically. And then in B, find the potential charge if the charge is moving from the I to F using C like this one. Okay, so the first we have to put Vf minus Vi. Okay, so the first is we have to check the work between I to C. So because of the cosinus theta, if we move from I to C is 90 degree like this one. This is the we move here, and then this is the E. So the D and E, the theta between D and E is equal to 90 degree. So the Vf minus Vi is equal to 0. Yeah, because the cosinus 90 degree is 0. So the I to C, the Vf minus Vi is equal to 0. So we only have to calculate from C to F like this one. So we can use these equations. Just like this one, the field is perpendicular to IC path, so there is no chance in the potential, Vf means Vi minus integral C to F E ds or minus integral C to F E cosinus 45 degree ds because of the angle between the D to E is 45 degrees. So we can get these equations minus E cosinus 45 degree integral CF ds. So we can get this equation minus E cosinus 40 degree dot D per cosinus 40 degree. So we can get minus ED. So this is similar. If we move the charge from one point to another point, so we have to check the movement or the shortest path of the object of the charge. So not the actual path. It's like this one. The charge only move from I to F. So this is the the movement of the charge. And in the second question is the particle move from here to here. But the final answer is we have only check the distance between the I to F. So this is the final two initial point. So we don't have to check the actual path of the charge. I have you understand of these explanations. And then this is the another exercise. What is the net electric potential at a point of P due to the four particle of if the F is zero at infinity? The key is 5 femtocoulomb and D is 4 centimeter. So here, yeah, you can easily by using the equation F is key key per r like this one. Okay, so the r is in variations because you have to, this is the fourth chart, so this is the 1 2 3 4, so we have the 4r here. So F is equal to key per 4 phi epsilon 0 multiplied by the first we calculate this one minus 1 per 2 dy minus, because this is the minus, and then second here minus 1 per d, and then this one plus 1 per d, and this one plus 1 per d. So we can use this equation, so we can get 5.62 multiplied by 10 point minus 4 volts. So this is how to solve this equation. So I think this is enough for the Gauss law and potential charge. Okay, for next week we have a quiz, but I will deliver the information later. So please check the AMAS frequently. Okay, good afternoon and bye bye. Thank you.